Hey BC Calc students, this is day 36 in your packet, and today we're talking about corollaries to the mean value theorem and anti-differentiation. Big day for us because so far we've been working forwards by finding lots of derivatives up until this point, and now we're finally moving on to talk about the concepts of anti-derivatives, which is probably no surprise here, working backwards. So to set the stage for what we're talking about, it says we're starting with the derivative of a function. We want to work backwards and figure out what's the equation that would represent the function f of x. So it has a little bit of a connection to the mean value theorem, because what does mean value theorem state? If we're continuous and differentiable on an interval from a to b, then there exists at least one c value such that the slope of the tangent f prime of c is equal to the slope of the secant through a and b. So some corollaries to that would be that if f of x equals c, if f of x is a constant, then the derivative equals 0 over the domain of the function. Okay. So we know that to be true, that when f of x is some sort of constant function, that the derivative is always equal to 0 then, for the slope of the tangent line at those values. So then what would the converse of that statement be? Well, logically, to find the converse of an if-then statement, you switch the order. So now it's going to say if the derivative is 0 for all values of x on the interval from a to b, then there must be a constant c such that, and this is a typo in the notes that you might want to fix quick. Your notes, I think, say f of x equals x, but it should say f of x equals that constant c for all values of x in the interval from a to b. So a quick way of summarizing that is saying, hey, if we know the derivative of something is 0, then we know that the original function f is a constant, and that's kind of where we're trying to build this up from, right? So we're trying to think about, if we know the derivative, how do I work up to getting what the original function was? So consider this set of functions, f1, f2, f3 of x. If we have x squared plus 8, and x squared minus 3, what do we know about the derivatives of all of those? So f prime of, or f1 prime of x, and f2 prime of x, and f3 prime of x. Well, if I find the derivative of every single one of these, don't they all turn out to be 2x, 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 2x? So that's kind of interesting, because the derivatives of all of them are 2x, but all the original functions are different looking. So if functions differ only by a constant, then what's the conclusion? Even though these functions differ by just a constant, then the derivatives are equal. Okay, so that's the conclusion there. Functions differ only by a constant, then the derivatives are equal. Is the converse of this true? So converse we just talked about was switching the order of the if-then. If the derivatives are equal, then will the functions only differ by a constant? And the answer is absolutely and unequivocally yes, that's definitely true. So the converse states exactly what I just said. If the derivatives are equal, then the functions differ only by a constant. So this concept here is kind of like thinking of it this way, that if I gave you the derivative first, this is kind of like knowing the answer. And what I want to work backwards to do is figure out what was the original question, which should really be standing out in your mind as the infamous game show Jeopardy, right? So here we go, Jeopardy. We probably need a little theme music here. Probably make this a little bit louder. Oh, how nice. Oh, guys, if you could only see me now, I'm totally bopping away over here to the Jeopardy theme song. Now, here's the interesting thing. When I make videos, I don't oftentimes say anything specific to what day of the week I'm recording, what year it is, but I feel like I can't get away with doing this video without giving a shout out to, of course, Alex Trebek. So this is the year 2020. And it is very unfortunate that Alex Trebek actually passed away about a week ago this year in 2020. So it's very sad because, to be honest, Jeopardy is one of my favorite game shows. I watched it a lot growing up, and Alex Trebek has been the host since I was born. He's been the host of that show for a very, very long time. So I know Jeopardy will probably go on from here, and I know you guys probably have seen Jeopardy at least once or twice. But to continue on in Alex's honor today, yeah, isn't it the concept of knowing the answer and then working backwards to find what the original function is? That's exactly what we're talking about when we find antiderivatives, okay? So if I know that the derivative is 2x, what's the original function f of x? Isn't that what we just did in the last set of examples, where all the original functions were something like x squared? But the thing is that it's not just x squared, is it? I mean, all of those functions that had derivatives of 2x, there were a lot of them. There was x squared, there was x squared plus 8, there was x squared minus 3. So how do we account for that then when we say, what is f of x? We say that f of x is x squared plus c. It's plus some constant, right? And this is called the constant of integration, which we'll get to know a little bit more as we go through examples. So we know that anything of the form x squared plus c will have its derivative as 2x, because of course the derivative of a constant would then become 0. But any function of families that has this general form x squared plus c, we know has that as its derivative. So for antiderivatives in general, f of x is an antiderivative of the original function of f of x if and only if f prime of x is equal to the function f of x, okay? So we're saying if we take the derivative of this and it equals this function f of x over here, then we know that we found the correct antiderivative. So what we're trying to figure out, and here's my whole Jeopardy column of antiderivatives here. If we take antiderivatives for 200, Alex, the answer is 4x. So if the answer is 4x, what's the original function that would have produced this derivative? Well, for anything that's a power function, we know that when we find the derivative, it decreases by 1 degree, right? According to the power rule. So I know at least has something to do with x squared. But what does the coefficient have to be out front such that when I drop that exponent down and multiply by it, that we get a result of 4? And it turns out that it's going to have to be a 2, isn't it? The derivative of 2x squared would be equal to 4x. So that's what I kind of want you to think about. Like, how am I going to get that to be a 4? Well, think about when I drop that exponent down, what times that value is going to give you 4? And in this case, it has to be a 2. Oh, and by the way, it's not just 2x squared. It could be anything of the form 2x squared plus c, plus some constant. Because when I take the derivative of the constant, that's going to go to 0. So you have to have plus c for sure. All right, what about 12x squared? Same logic. If I say the original function would have to be 1 degree higher, x cubed, 3 times what other constant would produce that 12 out front? Well, hopefully something standing out near minus 4. Okay, 4x cubed plus c is the antiderivative of 12x squared. All right, moving down the line. Maybe you've already filled these in because you got the pattern already. Okay, but something like 8x cubed up the power by 1. So now we're at x to the 4th. And what am I going to have to make the constant out front such that 4 times that number is going to give me an 8? So it has to be a 2 in this case, 2x to the 4th and then plus c. So can we start thinking of a rule in general here about how I'm going to develop what this new constant is? Okay, so when we increase it by 1, how do I look at the constant here and relate it to the constant here? And when I increase that power by 1, how do I look at the constant here and relate it to the constant there? And if you're making some connections starting, way back at the beginning of this antiderivatives category here, it turns out that when you up that power by 1, the constant in f prime of x divided by 3 is 4, isn't it? And similarly over here, 8 divided by 4 would be 2. So let's see if we can apply that same idea to this $800 answer over here. If I up the power by 1, that's 5. And then 15 divided by 5 is 3 as the coefficient out front. So if I have this defined as 3x to the 5th plus c, is the derivative of 3x to the 5th 15x to the 4th? Sure is, right? Drop the power down, you get 15x to the 4th. Exactly. So we're then breaking this down, of course, to what happens in general if we have something of the form x to the n. So the rule is when we're finding antiderivatives, we're going to up the exponent by 1, so we get x to the n plus 1. And then the coefficient out front, which I guess in this case is just denoted by 1 at this point, is divided by that new exponent. It's divided by n plus 1, right? Up it by 1, divide by 5, that's how we get 3. Up by 1, divide by the 4, that's how we get the 2. So it follows that same pattern, plus c. And what you can actually think of this now as being is when we write that last rule, this is kind of the anti-power rule. We have our power rule for derivatives, so working backwards, this is, I guess, what you would call the anti-power rule. All right. All right. What about x to the negative first? That wasn't in our original list. So if we use the anti-power rule, what would happen? Well, I would up the power by 1 and then divide by that new exponent. So if I up this by 1, we're now at x to the 0 over 0. X to the 0 over 0? Ooh. I'm like, I have no idea what that means. Okay. Well, the answer is not yet. We will eventually get to the antiderivative of this, x to the negative 1, later on, but we're not quite there yet. So the anti-power rule so far holds true as long as n is not equal to negative 1. Okay, that might be, one of our few exceptions that we have until this point. But, hey, we can even extend this to thinking about, in this chart here, if we have the derivative in the left column, thinking about what f of x is in the right column. We can extend this for things that have fractional exponents. I mean, we know radical x to be x to the 1/2. So if I up the power by 1, now it's x to the 3/2 power. But then think about this. This coefficient of 1 is going to have to get divided by the new power of 3/2. Well, 1 over 3/2 is like multiplying by 2/3. So the antiderivative would be 2/3 x to the 3/2. Don't forget about plus c. Okay, similarly down here, if it's 1 over the square root of x, just write it as x to the negative 1/2. So the antiderivative, up that by 1, we're now at 1/2. So it's x to the positive 1/2. Take the coefficient out front and divide by 1/2. Well, dividing by 1/2 is like multiplying by 2. So therefore, we get 2x to the 1/2 plus c. And you can really keep going for all these examples. If at any point you want to kind of challenge yourself and hit pause and try some of these, you'll notice we're getting into definitely some trig-ish territory down here. But go ahead and try them. I mean, the next one, same idea. Make it x to the negative second. Up it by 1. That's still okay because we have negative exponents. Now it's x to the negative first. And then if I take the 1 out front and divide by negative 1, you get negative 1 x to the negative first. So we would probably write that as negative 1 over x, right? We have negative 1 x to the negative first. Bring that down to the denominator, make it x to the positive first, and then plus c. Of course, with any of these, you can find the derivatives here and check that when working backwards, you're going to go ahead and get the original f prime of x that we're defining over here. All right, cosine x. Think about this carefully. We want to think about this is the derivative of what function? You guys should be really familiar with this if we're up on our trig derivatives. Well, cos is the derivative of the function sine x. So if you have anything of the form sine x plus c, we know that f prime of x is cosine of x. Okay. All right, secant squared. What is secant squared the derivative of? The derivative of the function tangent, right? Tan, derivative secant squared. And with the 2 that's out front, we can just carry that to the original f of x, right? That coefficient out front wouldn't affect finding the derivative there. So 2 tan x and then plus c would be f of x, capital F of x, if the derivative is 2 sec squared. Okay. How about 5 sec tan going on down the line here? 5 sec tan, derivative is sec tan. That means the original function is secant plus c. And now in these last two, we have to think a little bit harder about this one because it's not just as easy as thinking about the fact that, this is the function sine and that the original function must have been, hopefully you're thinking negative cos, right? In order to get positive sine as the derivative, negative cosine would have to be the function over here. But we have to think a little bit tougher because it's 3x on the inside. So instead of thinking about what the chain rule does, you have to kind of think like anti-chain rule here when you have that changed quantity 3x on the inside. So what would the chain rule have done if I was finding the derivative? Chain rule would say, multiply by the derivative of the inside. So instead of multiplying by 3 when I'm working backwards, well, maybe it would make sense to divide by 3 to work backwards over here. All right, so instead of taking the 6 and multiplying by 3, I'm going to divide by 3, and that's going to make it a 2 out front. But like we said, the derivative of, if this is the derivative sign, then the original function is cosine, and keep the inside the same, 3x plus c. Now, because we're so good at trig derivatives, and this one isn't too hard anyway, think about what the derivative of this is. Derivative of cos is negative sign, so negating that makes sense. Oh, and if it's cos of 3x, with the chain rule, you would do times 3 to get that to eventually become a 6. So you really want to make sure that if you're stuck and you're like, oh, do I multiply, do I divide? Well, when I'm working backwards, you do the opposite, so we'll divide, okay? And then from there, once I've made that decision, just double checking that when I find the derivative, we get back to the f prime of x column. All right, so in the last one, same type of deal. Well, we know that the cos is the derivative of sine. But thinking about what that coefficient is out front, don't multiply it by a half. You're really dividing this by a half, if we think of that anti-chain thing again. So 5 divided by half makes this a 10 in front of sine of x over 2 plus c. Okay, we've got some really solid practice in. I would recommend that, again, maybe you try some of these next ones on your own. We haven't done any yet in the notes that you've had to find the sum or the difference of functions here, but you're going to treat them individually, right? Just like you can find the derivatives of each of these terms individually, you can find the antiderivatives of each individually. So if you want to hit pause, I'm going to go over them right now, but we're going to wrap up this lesson pretty quickly here with these last couple of examples. So the idea is if this is the derivative to get capital F of X, we're going to up these by 1 and then divide by that new power out front. So this would be 1/6 x to the 6th, or just x to the 6th over 6, right? So up it by 1, divide by the new power. Similarly, over here would be plus x to the 4th over 4, and then again, plus c. We need that. Okay, so what if there's a 3 out front? Well, if I up it by 1, we get x to the 5th, and then divide by the new power. So now it's 3/5 x to the 5th. Minus, this is now x cubed when I up it by 1, so minus 5/3 x to the 3rd plus c. Okay, and then for the final example here, when we treat these individually, cosine of 2x, if the derivative is cos, the original function sine, but with that anti-chain rule step, we're not going to multiply by 2, we're going to divide by 2 on the outside. So it would be 1/2 out front of sine of 2x. Okay. And then from there, the derivative, if it's negative cosecant squared. So negative cosecant squared, what's that the derivative of? It's the derivative of cotangent. Because remember, tan is sec squared. So cotangent would be negative cofunction, negative cosecant squared. And there's no chain rule step here because there's no change for the frequency of x on the inside. So this would just be minus 3 cotangent of x plus c. And of course, if I work this direction, we're going to get that to be f prime of x. Last thing we're going to do in our day 36 notes is solving this differential equation. So we have dy dx equals 2x, and we're going to take a look at what the general solution is, which is what we've been doing all along today, versus finding a very particular solution. So we started with this premise today. If the derivative of a function is 2x, the function that satisfies this would be f of x. Okay, and when we work backwards, we use the capital F of x here, equals x squared plus c. Right? Anything of this function of families would satisfy the equation such that dy dx equals 2x. So the general solution would be a whole family of curves that represent x squared plus c. I mean, if we think about x squared plus some constant, that could look like this if the constant is 0, but it could also look like this if the constant is positive. It could look like this if the constant is negative, right? It could be any of these curves in particular. Something that's going to have that y-axis symmetry, just different by some sort of constant there. Well, suppose we have some initial conditions. Okay, so these initial conditions here are, we know that when x equals 1, y is equal to 7. So then it says find the particular solution to dy dx equals 2x. So going back to f of x equaling x squared plus c, we know that when y is 7, that x is 1. So we can find the particular function of this family x squared plus c by really quickly getting that c equals 6. So the equation y equals x squared plus 6 is the particular solution to this differential equation such that the derivative is 2x, specifically when x is 1 and y is 7. So that was a pretty easy initial condition to sub in and find, and not that that will get more challenging, but sometimes rather than just finding the general solution with plus c at the end, we might be given some initial conditions to sub in to find a very particular solution that solves that differential equation. So that's it for our introduction to anti-differentiation. So much more to come with this. It's really exciting that we're getting started with our really the second key aspect of the course of calculus. Derivatives is a big part, anti-derivatives just as big of a piece of the puzzle. All right, if you have any questions, let me know next time I see you.